So you might be asking that if momentum is such a fundamental physical quantity, then why is it that we haven't talked about it at all before now? And the argument that I'm going to make is that we have talked about it before, we just haven't done it by name. Because what Newton's laws fundamentally are doing is they're keeping track of the momentum. So when we talked about Newton's first law initially, right, when we introduced it, we said, hey, objects at rest remain at rest and objects in motion continue to move in a straight line at a constant speed unless they are acted on by a net external force. Well, we can reframe this so that Newton's first law now says objects at rest remain at rest and objects in motion continue to move in a straight line at a constant speed unless their momentum is changed by a net external force. And so what does this reframing get us? Well, basically what it does is it says that if you have an unbalanced external force, that will act to change an object's momentum. So if you think about the situation where an object's mass doesn't change and its velocity is constant, well, since its momentum is mass times velocity, if neither of those two things change, then that means the momentum also has to be constant. The momentum being constant, that means it doesn't change. And from the impulse momentum theorem, if the momentum doesn't change, that means that the net impulse acting on the object has to be zero. And because impulse is defined to be a force acting over some time interval, you get your net impulse to be zero by having the net force be zero. And if the net force is zero, that means you get no acceleration. On the other hand, if your object's mass doesn't change, but its velocity does, then your momentum, the momentum of your object is changing. And again, from the impulse momentum theorem, that means that there has to be a non-zero net impulse exerted on the object. So if the momentum changes, then there has to be an impulse. And that impulse comes from the fact that you have a non-zero net force, an unbalanced net force that acts on the object over some chunk of time. In doing so, that causes the object to accelerate. So you have some non-zero net force that acts over some chunk of time that generates an impulse and it causes the object to accelerate. So this is the way that we can reframe Newton's first law. Well, we can do the same thing for Newton's second law. So again, Newton's second law we've talked about is the way to quantify how the net force acting on an object relates to its acceleration. Well, if I think about the average net force, again, that's just the mass times the average acceleration. And the average acceleration, of course, is delta v over delta t, the change in velocity over the change in time. And all I'm going to do is say, well, if the mass doesn't change, then I can tuck that back inside the delta as well. And so I've got this quantity that says delta mv over delta t. Well, of course, mass times velocity is the momentum. So you can see that I can rewrite Newton's second law and at least talk about it on average as saying the average net force is equal to the change in momentum over the change in time. And so there are a couple things that, again, this lets me do. One is it says that if you change either the magnitude or the direction of an object's momentum, that requires an unbalanced net external force to act on the object over some amount of time. And again, Newton's second law gives you the way to relate those three parameters. It also gives us the impulse momentum theorem, right? So we sort of brushed over this in the moment, but here's where the impulse momentum theorem really fundamentally comes from. So notice if I take that delta t term in my Newton's second law equation and multiply it over to the average force side, then I've got the net average force times my time interval. Well, that defines what the net impulse is. But Newton's second law says that also has to equal the change in momentum. So this is where, our impulse momentum theorem is really just rewriting Newton's second law in terms of momentum. So we've, up until now, been working plenty of Newton's second law problems. Well, we're going to continue to work Newton's second law problems. We just might choose to do them in terms of the impulse momentum theorem. And there's some particular conditions that we might want to choose to do this over. In particular, situations where the forces acting on the object are complicated, we haven't dealt with those using Newton's second law yet. Now we can by focusing on the object's change in momentum. So one way to sort of think about what we're doing is that we're taking Newton's second law and we're basically adding another way to work a Newton's second law problem. So up until now, we've worked the net force equals ma problem, and all we're going to do is work our impulse momentum problem that says I can relate the net impulse to the change in momentum, and that can also be used to relate, and I can also relate those things to the net average force acting on my object over some chunk of time. And so when is it that these two sort of different types of problems become useful? Well, the problem that we've worked up till now has been particularly useful when we've had constant forces. Again, those constant forces have acted to give us a constant acceleration. And so we've worked a vector addition problem. We've added all those forces up. We've said that's equal to ma. We've gone and solved for the acceleration. We may have come back and added on the kinematics piece to figure out how that's affected the motion. And the drawing we've made to work that problem has basically been a single free body diagram of the forces that, because those forces are constant, that diagram hasn't changed. Well, what the impulse momentum theorem view of Newton's second law is going to let us do is it's also going to let us work Newton's second law problem where the forces are complicated. Because again, we've said I can sort of ignore that complication and just think about what's going on with the average force, because that's going to give me the same impulse. This now becomes a vector subtraction problem, because what I'm going to be interested in is subtracting the momentum vectors. So unlike in my F net equals ma problem, where we tended to know what was going on with the forces, right? That was clean enough. We knew what was going on with the forces and paid attention there. Here, what we're going to say is these forces are complicated, so I'm going to pay attention to the momentum vectors. And in this case, I need to subtract them because delta P is a momentum subtraction problem. So I'll end up making two vector diagrams. I'll draw both my initial and final momentum vector diagrams so I can break those up and do the vector subtraction. So we're going to continue to work Newton's second law problems. We're just going to be able to add this additional layer by adding in sort of this new style of Newton's second law with our impulse momentum theorem problem.